Okay, guys, I'm hoping your second day on these sections made it seem a little bit more easy. Hopefully you looked at the hints. These came from the 6-2 notes, and you should have made a table of values. I probably am -2, -1, 0, 1, and 2. I think those work pretty good. Now, you're going to raise 3 to each power, and I believe, I'm rounding a little bit, 0.11, 0.33, 1, 3, and 9. So I need to be able to fit up to probably 9 on my graph. Okay, so I think I'm going to have to draw the axes way down here. Okay. On the -2, I'm just barely above the axis. On the -1, I'm about a third of the way up. On 0, I'm on the 1. On 1, I'm on the 3. And on 2, I'm all the way up to the 9. And like that. You have the x-axis as the asymptote. Notice the domain could be anything, but the range has to be bigger than 0. All right, then you want to do the same thing for the next two. When you put this in the calculator, you can either do parentheses 1 divided by 4 to the power, or I just use 0.25. That worked really nice. And the answers I got were 16, 4, 1, 0.25, which of course is a quarter, and 0.06, which is almost on the axes. Oh, I have to be able to make it up to 16, so I think I'm going to end up counting by 2s. 2, 4, 6, 8, and then up to the 16. All right, so the -2 was on the 16, the -1 on the 4, the 0 on the 1, and then these are, again, getting closer and closer to the x-axis, which is its asymptote. And then the last graph, -2 gave a 5.5 repeating, -1 gave a 6.6 repeating, and then 0, 8, 1, 9.6, and 2, 11.52. I think I'll count by 2s again. 2, 4, 6, 8, 10, 12. Okay. -2 is going to be the 2, 4, 5.5 right about here. And then -1 is right about here. 0 is on the 8. And then 1 is on the 9.6. And 2 is almost to the 12. This one's kind of hard to tell what's going on. It looks like it's increasing here. I'm not quite sure where the asymptote is. So I think what I would probably do is try a few more values, like try -3 and -4, just to see if that gives us a better idea of what's going on in this graph. So let's try those. If I did 8 multiplied by 1.2 raised to the -3 power, I got about a 4.6. And then with the 4 negative, I got about a 3.8. So you can see it's kind of settling down right about on the 4. It would actually be something like that. Okay, and now for the next group, you kind of have to work backwards. They gave you the graph. Let's look and see if from the graph we can come up with some nice points on the table. If I look, I believe they're counting by 6, so that makes the 0 on a 3. So that's a pretty good point. These down here, it's really hard to tell. The 1 I can see is a 6, the 2 I can see is a 12, and the 3 I can see is a 24. That's great, because I can now tell from my chart that it's doubling every time I'm multiplying by 2. So my function has an initial value of 3, and then I have a 2 to the x power. Okay. Now number 4, I have the table. I don't have the graph. I can see that this one is also doubling each time. My initial value was 5, and then it's also 2 to the x. All right, I'm curious to see what you did on number 6. It wasn't as easy to tell on this one. If I look at my chart, the -2, it's not there. -1, I can kind of tell though, is right here. That's on a 10. And the 0, I can kind of tell. This is 4 and this is 6, so that's about a 5. Now, when I look at the 1, I really can't tell. It's just slightly over 2, and then 2 is like in the half range. So I really can't tell. So I only have those 2 nice points to work with, and notice that it's dividing by 2 or multiplying by a half. So I'm going to think that the function has an initial value of of 5, and then it's 0.5 to the x. Now before I just assume that's correct, let me try the 2 or the 3 or the 4 to just see if it makes sense. So if I do 5 times 0.5, which I'll raise to the second power, I should be about 1 1/4. And that kind of makes sense. I would be at about the 1 1/4. All right, not a super good problem. These are definitely more like you would see on a quiz. Okay, so number 7, you didn't really need to do that big long formula that we had because they actually gave it to you. It's right here. And they're just wanting a 15-year balance. But it is, sorry for the dog, it is where you have just 1 year, so you just need to put in your calculator 5,000 multiplied by 1.05 to the 15th power. Okay, that should give you $10,394.64 for a $5,000 investment. Notice that in 15 years, it's more than doubled. That's pretty cool. Okay, moving on. These are slightly different than the ones on your homework, but not really. On the homework, they gave you the growth factor. The growth factor, remember, you have to take the initial whole 100% and add it to these values. Okay, so your function would be the initial value of 2,000 and then your growth factor of 106%, which is 1.06. Okay, now if you didn't get that right, go ahead and pause the video and try 9 and 10 again. Okay, so for number 9, you have an initial value of 50, and the growth rate is 75%. So the 100% that you have plus the 75 makes it 1.75. And then number 10, your initial value of 40, 100% that you started with, and then 100% growth is 200%, which is just 2. Okay, now these are the ones where you want to write the function and then put them into the calculator to get the approximation. So this would have an initial value of 1,000. Now it decays by 20%. So 100% take away 20% is 80% or 0.80. Now I want to know where that answer is 500. So recall, you're just going to simply go into your calculator and enter in your equation. 1,000 parentheses 0.8 raised to the x power. Okay. Now, you want the table for that value. So we want to go second and then table. Now I'm looking for the table somewhere where it's 500. Notice mine came right up on the 6. You might have wanted to go back to the table set and started at the 0. Or I think you can just arrow up from here. No, I guess you can't. So let's go to second table set, setting my table to start at 0. Now, let's look at it. Okay, that's a little better. Can you see that the 500 is going to be here or here? It's going to be between the 3 and the 4. So my answer is going to be a 3-point something. Okay, let's see how close we can get. Let's see, clear, no, quit. Let's quit. Second quit, 1,000, and then parentheses 0.8. Let's try the 3.5 power. I think I need to be a little closer to the 3. Let's try that, 1,000. And then 0.8 to the, let's just do maybe a 3.1. Oh, that looks great. 3.1 it is. Okay, now at this point, if you did not know how to do that, now that you've seen it, stop the video and go ahead and try these two, because the next screen you see is going to have the answers. Okay, there's the answers. Check to see if you got them right. Here's the equation. Make sure you understood that, because you would have 100%, but it would decay 7%. So that's 93%, which is 0.93. And the best answer you could get, I got about 20.7. You know, I would say if you're in the 20.5, 6, 7, or 8 range, that you did a pretty good job approximating that one. 13, if you have 100% and you decay 12.5%, that puts you at 87.5%, which is 0.875. Put this in the calculator. Now this one, make sure you go back and you start your table back at 0, because remember, it's up here in the 20s from the last problem. And you're going to get an answer about 7.4. On that one, the 7.5 gave me 440. And the 7.6 gave me 434. But when I went down to the 7.4, that worked pretty good. I got 446. But again, if you're in the 7.45 or 6 range, you probably did a great job on that one. Don't understand that? Make sure you log into the Zoom help session on Tuesday, and Ms. Meyer can go through that with you some more. All right, number 14. You have an exponential function, and you have the initial value and the decay rate. So let's just go ahead and get that function written down. If it decays 15%, you're left with what, 85% or 0.85? Now, you want to do a rate of change from this interval and this interval. Okay, so I need to know what it is at 0. So at 0, I have 500 times 0.85 to the 0 power. Remember, anything to the 0 power. Okay, I had an error, so I'm going to go ahead and edit it. Anything to the 0 power is 1. So 0.85 to the 0 power is 1. So 500 times 1 is 500. So at 0, this function is 500. Now at 4, you would enter in your calculator 500, 0.85 to the 4th power, and you would get 261. So from 500 to 261, it went down 239. Now, from 0 to 4 is 4. That's the difference. That's the change there. So 239 divided by 4, and that interval, it's going down 59.75, or it's going down 60. Okay, now I need to check the next interval from 4 to 8. Well, I already did the 4. That was the 261. At the 8, you would put in your calculator 500 times 0.85 to the 8th power, and you'd get 136. So from 261 to 136, it's still going down. This time it went down 125. From 4 to 8 is still 4. Divide, and you can see it went down 31. So now the directions wanted you to compare. Well, in the interval from 0 to 4, it went down 60. In this interval, it went down 31. So it decayed faster from 0 to 4. And you could actually say that it went down about 31 faster. Okay, the last question. Harrison's comparing two CDs, one at a local institution and one at an online institution. All right, he needs to know who's going to give him the better deal if he's just going to make one flat deposit. Okay, let's think about the amount that he's going to get at the local bank. Well, he's going to get his $5,000 principal. And then remember in here was 1 plus the rate, which is 6%, that's 0.06. Locally, it's compounded annually, so that's 1 time a year. Remember, the exponent is that number times how many years he's going to leave the money in. Now, this problem didn't give us how long his investment is. And if we wanted a specific dollar amount, we would have to know. But if you think about it, compounding quarterly means you're going to get money 4 times a year, where annually only once. So the compound quarterly is automatically, we know, is going to be the better deal. Okay, and that's the online. So the answer is that the online institution is the best deal. Now, let's go ahead and work this example out for, let's do it for 10 years. That way we can actually see that that's correct, and also because that's what you're going to need to do on the test. So let's put in 10 years. So we have a $5,000 investment, parentheses, 1 plus 0.06 divided by 1, and raise that to the 10th power. And you're gonna... Sorry for the little glitch. I ran out of memory and had to go in and delete some old videos. Okay, I'm sorry. You have entered into your calculator 5,000 and then 1.06 to the 10th power, and you have $8,954.24 after 10 years. Now, go ahead and do that for the online compounded quarterly, putting a 4 here and here. And that is something you probably should go ahead and pause the video to make sure that you actually know how to do that. All right, 5,000, parentheses, 1 plus 0.06 divided by 4, closing the parentheses, and then raising the whole thing to the 40th power is $9,070.09. So you can clearly see if the interest rate is the same, you're going to have more money when it's compounded quarterly. That's the better deal. Anytime you can get someone that owes you money or that you're going to get money from an investment, you want it compounded as many times as you can get it. However, if you owe someone money, you really don't want it compounded many times at all. Okay, we're going to move on to the next section for the next day.